co-host, but normally it's...
So, welcome to this webinar on low carbon cost effective hydrogen solutions. We're delighted to have two speakers with us today. The webinar series is part of our hub on hydrogen integration for accelerated energy transitions. And we're very interested in the potential role for hydrogen moving forward as part of the energy transition to net zero. So for colleagues joining the call, if you can stay muted, and we'll take questions at the end after both speakers. Thank you. Feel free to keep cameras on or off. It's up to you. I'll introduce our first speaker. So Dr. Yongliang Yan is a research associate in the School of Engineering at Newcastle University, working on the scaling up of novel chemical looping concepts for low carbon hydrogen production. Dr. Yan's research interest is firmly in CO2 capture technologies, clean hydrogen production, cost-effective energy storage, probabilistic techno-economic performance assessment, and machine learning in materials science and energy engineering. So I'll ask our first speaker, Dr. Yongliang Yan, to go first, and I'll introduce our second speaker once Harry's finished. Thank you.
Yeah, thanks, Sarah, for the introduction. Good afternoon or good morning, everyone. So my name is Yongliang Yan. I'm currently a research associate at Medical Group. Today I will talk about chemical looping technologies for clean hydrogen production. I will focus on the sorption enhanced steam methane reforming and the chemical looping water gas shift reactor. So as we know, hydrogen is very useful for oil refinery, ammonia production, and chemical production, and also low carbon hydrogen can be a very attractive clean energy carrier for decarbonization. Currently, we need the hydrogen production is about 90 million tons. But if we want to achieve net zero by 2050, we need hydrogen 200 million tons by 2030. So according to the IEA report, so we should because the current hydrogen production is dominated by the steam methane reforming, so which is used fossil fuel and generated lots of CO2 during the hydrogen production. So we have to focus on the low carbon hydrogen production technologies like water electrolysis, use the renewable energy, and also we can integrate the carbon capture technologies with fossil fuels. So what my research background is focused on the high temperature solid looping for CO2 capture. So chemical looping is very versatile platform that can be useful for the clean and efficient fuel conversion or chemical production. It is well known as the chemical looping combustion, so which we use a mantle oxide as an oxygen carrier to carry the oxygen from the air reactor to the fuel reactor, and then the fuel reactor with the mantle oxide inside of the air. So you at the outlet of the fuel reactor, you got CO2 and the steam can be easily condensed. So you got the high purity CO2, which can be for the utilization or storage. So it's also called unmixed combustion. So you don't mix the fuel with the air, which in the air you got about 80% of nitrogen. So that will increase your energy penalty and the cost to separate the CO2 from the flue gas. So another form of the chemical looping is called the castle looping. So what we do the same looping here, but we use the calcium oxide as the solvent. So we could capture the CO2 from example from after the power plant, so the flue gas from the power plant. So we capture the CO2 to the carbonation, and we use the solvent to the consumer, and then we regenerate the solvent and use for the next cycle. So today I'm going to talk about how could we uses two forms of chemical looping to integrate for the with the steam method reforming for low carbon and high purity hydrogen production. So as I mentioned, the current hydrogen production is dominated by the SMR, so which also produced about 2.6% of global CO2 emission. So if we check the traditional SMR process, so first we got the natural gas reforming, so we produce syngas, and we need to maximum the hydrogen production, so we need to have a series of water gas shaped reactor. So to convert the CO to the CO2, and then we have hydrogen production. We maximum the hydrogen production, and then if we want to increase the purity of the hydrogen, we need to have a costly pressure swing of the sorption unit to have the high purity hydrogen. So what we could do for the chemical looping, the first configuration, we can integrate the cathode looping with the steam method reforming. So it's a simple way is when we do the steam reforming, if we remove the CO2 and according to the equilibrium law, we can shift the reaction to the right-hand side. So we have more hydrogen production. So this is the benefit for the sorption enhanced steam method reforming. So in the steam reformer, we can use a fluidized reactor. We put the catalyst and the solvent in the reformer. So during the steam reforming, we can do the in-soot CO2 capture. So then it will shape the reaction to more favorable for hydrogen production. And then it's very easily for gas solid separation. So you have the high purity of hydrogen, and then the solvent can be regenerated in the consumer, and then the regenerated solvent can recirculate to the reformer for the next circle for CO2 capture. So in this process, we can, for the sorption enhanced steam method reformer, you combine the traditional reformer with the water gas shift reactor and also the pressure swing of the sorption unit, and as well as the CO2 capture. So in a single process, you can maximum the hydrogen production and as well as for the CO2 separation. So the benefit for the SESMR is we have the high yields of hydrogen. So, and also the reaction temperature is lower compared to the traditional SMR. So because the steam method reforming is endothermic process, so you need a burner to provide the additional heat for the reformer. But for the sorption enhanced steam method reforming, you have the XO reaction for the carbonation, which can provide the heat for the steam method reforming. And as I mentioned, we have in-soot CO2 separation, so you don't need to separate the unit for the purification of hydrogen. And of course, we capture the CO2, we have low CO2 emission. And because we reduce the size and reduce the carbon capture block for the SMR, so which ideally we have the lower capital and operating cost. We also have some challenge for SESMR. So the most important is the activity for the solvent when we recycle the materials, our circle and circles. And also we need to regenerate use the solvent. So that is a high energy intensive process. So we need to carefully for the height integration and optimization to maximum the CO2 capture. And we also don't know the economic performance of this kind of technology. So what I did, to overcome these challenges, what I did is I used Aspen Plus to build a process simulation for different configuration of SESMR process, which integrate with oxyfuel combustion, chemical looping combustion, and biomass combustion for the consumer. As I mentioned, because the consumer is endothermic, we need energy input. But if we integrate with house-built combustion or chemical looping combustion, we can use low carbon heat for the SESMR process. And I also built a economic model to evaluate the economic performance of different configuration of SESMR process based in the UK. So I evaluate the level cost of hydrogen, cost of CO2 avoided. So as say in this table is summarize the key performance for the model. So as you can see, with the different configuration, we can capture the different CO2 in the hydrogen production process. So with the different cost from 1.9 pound kilogram hydrogen to 2.8 based the different CO2 capture efficiency. And I also build a model to check the economic performance of different configuration of SEM process with the assumption of the different hydrogen selling price in the UK. So if we have if the hydrogen selling price in the UK over 3 pounds per kilogram, so you can, as you can see, most of the SEMR process can be revenued in about 5 years. So this work provided a techno-economic performance of different SEMR. That's why I say this technology is very promising for low carbon hydrogen production. And if we use the biomass as a feedstock in this process, we can even achieve the carbon negative CO2 emission for hydrogen production. So this is the first technology I want to mention for the sorption enhanced steam acid reforming. So another one is I'm currently working in the Newcastle for the chemical looping water gas shift reaction for low carbon hydrogen production. Again, if we check the steam reforming process, as I mentioned, because the conversion for the steam reforming, so we got CO, we need a series of shift reactor to maximum the hydrogen production. But this is a mixed reaction. So when you have the maximum theoretical conversion is 50%, so you mix the CO2 with the hydrogen. So what we could do, we could also accept the chemical looping concept in the water gas shift reaction. So what we do here is we separate the water gas shift into the traditional water gas shift reaction into two separate process. But first we can oxidize the materials with steam. So we got the pure hydrogen production, and then we reduce the bed, use the CO, we have CO2 production. So in this chemical looping water gas shift process, we produce the high purity of hydrogen and CO2 in the separate process. So we don't need to use the additional carbon capture process or pressure swings process for the high purity of hydrogen production. And also, as I mentioned, if we for the traditional chemical looping mantle oxide process, so if we achieve the maximum conversion is about 50%. But if we use the non-stoic oxygen carrier materials, which can have a various of oxygen potential, so the novelty of this technology, what we do, we feed them, as the right-hand video show, we feed steam and the CO in opposite directions for the bed. So we not fully oxidize or reduce the bed. In the end, we have the pure CO2 and the steam and the hydrogen production without the equilibrium limitation. So in the theory, we could achieve 100% of conversion. So for the integration, what we do, we don't need the water gas shift reactor block and also the PSA and CO2 capture block. We can integrate them directly after the reformer for low carbon hydrogen production. So this concept was was first validated by my colleagues, so which use a chemical memory reactor, which is a packed back reactor with a gas switching technology, and use the in-suit XRD to validate the bite and provide the various oxygen potential for chemical looping water gas shift to produce a high purity of hydrogen production. So my job at Newcastle is I will build this larger packed back reactor with gas switching technology. So the previous reactor will only test the 2 grams of material at 5% of CO steam. So this new reactor I designed and built it, which is aimed to test about 2 kilograms of material at the industrial process condition for high purity of hydrogen production. We also need for the sub-pellet project, we also need to manufacturing the materials for this big reactor. So we use mixing, extrusion, vaporization process to make the pellets, kilogram scale pellets for this process. So as you can see, we got the pellets at the end. So we do some material characterizations and some redox tests. So we test the 50 circle and 1000 circle, and the material is really stable, and we didn't spot any carbon deposition. So for the future work, we will test the new build reactor by this summer, and we also, after the initial lab test, we will do the long-time operating test at our industrial partners. And we also want to do some techno-economic analysis for chemical looping water gas shift to find that this technology is compatible for other low carbon hydrogen productions. And all the results I presented today is published in those journals. If you want some detail, you can have a look. So yeah, thank you for your listening. So I will answer your question at the end of the presentation. Thank you.
Thank you very much, Harry. So we'll move on to our second presentation and keep any questions at the end. But our second presentation is by Dr. Hossein Ameli, who's a research fellow at Imperial College London. Hossein's research is mainly focused on the role and value of hydrogen in supporting cost-effective transition to lower carbon energy systems. He was a contributing author in the Intergovernmental Panel on Climate Change Working Group 3 and contributed to many scientific papers as well as research projects related to the energy transition, including projects for the Committee on Climate Change, for Government Department BEIS, and for National Grid. So I'll hand over to Hossein now. Thank you.
Thanks, Sarah. Good afternoon, everybody. I hope you can see my screen, the full screen, right?
Yes,
Perfect.
we can.
Okay. So the topic that I want just to have some discussion on is the role and value of hydrogen in supporting cost-effective net zero futures. Actually, it's kind of a bit different than what Harry presented. This one is more looking from the whole system perspective, that what is the value of the hydrogen that can support the net zero targets in the future. So just the content of the presentation is on, first I introduce some hydrogen strategies around the world, then how the value chain of hydrogen would be, the production, transfer and storage technologies, as well as at the end, just some brief results on the whole system benefits of integrating hydrogen to the system will be presented. So if I want to just to give some idea on what is going on in the world, many countries already established their, let's say, hydrogen strategies for the future. As you can see in Canada, obviously in the EU, UK, Russia, Middle East, Japan, and also Australia, all of these have kind of hydrogen strategies in place. And let's say around 50% of global GDP countries already have this national hydrogen strategies. So that is kind of showing the importance of hydrogen for around the world and all the countries. And if I want to go into more detail of the Europe and the UK case, we have this European hydrogen backbone. And the idea mainly here is to kind of use, because for the long distance transport of hydrogen, pipelines are kind of the most efficient option. And the idea is kind of to use the existing natural gas infrastructure, which is available already in Europe and in the UK. The idea is to probably we can almost have 70% of them can be repurposed. Instead of injecting natural gas, we transport hydrogen. And also, obviously, we need to build some new hydrogen pipelines. And this is the European Hydrogen Backbone, actually. It's a report published in 2021, and they're estimating that the cost of kind of repurposing this natural gas pipelines to hydrogen would be around 10 to 20 euro cents per kilogram of hydrogen. And then going to much more detail now in the UK, the plan is that's the National Grid plan, that the hydrogen roadmap to 2050, and they're just having different plans for different years. And as you can see at the bottom, 2045, the idea is that we have this national hydrogen transmission network, which means that kind of in the transmission level also we have this hydrogen network, and the repurposing of the existing gas infrastructure is what they are setting to kind of have as a target in order to use that in terms of kind of for reduction in the cost, investment costs, and so forth. So now let's just move on after having just these hydrogen strategies. The hydrogen value chain, obviously it's consists of the production side, the transport storage side, and also the utilization. The production can be from different routes. One of them is the SMR, let's say the steam methane reforming, which Harry presented in more detail, the enhanced technology that is kind of working on, which we call it the blue hydrogen if it's gonna come with the carbon capture and storage. And we have biomass gasification. That is also another interesting route, because this can provide also negative emissions, let's say, in order to balance the emissions from the hard to decarbonized sectors. In order to reach the net zero in 2050, this BECCS can play a major role, actually. And also, obviously, the other route, net zero, let's say low carbon, zero carbon route, is the green hydrogen production through electrolysis, and that can be mostly from the electricity from the grid or from the renewables, excess of renewables, nukes even. All of this can be, as long as electricity is the input, the green hydrogen can be produced through that process. And then for the transport and storage, we could have pipelines. As I mentioned, for long distances, pipeline is the best option. And also we could ship that through vessels and trucks, and that can also be converted to other sort of hydrogen-based mediums such as ammonia. And we should have obviously storage facilities underground and overground, which I'll just explain a bit later. And the utilization would be in various applications, which is transport, industry, buildings, power. So just here some rough kind of estimations on how the hydrogen production technologies, what are the efficiencies, the carbon intensities, and the capex. Let's say the cost of producing hydrogen like this is just here presented. These are kind of the routes which are low zero carbon production technologies, from SMR with CCS, then advanced gas reforming, which is the ATR, from coal gasification with CCS, biomass gasification, and also 3 technologies for the electrolysis, including alkaline PEM and solid oxide has been here presented. And also we have another method of producing hydrogen, which is called the pyrolysis, which is the turquoise color. They have just different colors, and which is kind of splitting the methane into the hydrogen and solid carbon, which is kind of, but still is not, let's say, been commercial broadly, and it is still in the development and research and development phase. Just hydrogen storage technologies. First of all, we have line pipe, which is one of the important aspects in our modeling. That is actually line pipe is the storage of the gas within the pipelines. And this is actually the idea of line pipe, is that since the transport of hydrogen takes time, it's not like electricity. So we need to have, in order to meet this demand in time, we need to kind of have this capability of having this storage in the pipelines in order to meet the rapid changes in the demand and supply. So that is one of the main storage technologies or storage aspects that we have, and also over distributed above ground storage, salt caverns, which are very important to have for the within seasonal kind of storage again, and also this use oil and gas fields. And just to here at the bottom, you can see the figure that's just showing that what can be the capacity of these different technologies, and also the duration of discharge, which, as you can see, we can have from hourly discharge, line pack, and overground storages to seasonal storage, which can be also this use oil and gas field. And the capacity can go up to 10 gigawatts, for example, for depending on the technology. So what actually my focus is on integrated analysis of hydrogen and electric systems. But why is it important? Because as we mentioned, it's more likely that hydrogen will replace natural gas in the infrastructure. For example, here the focus on transport. So here we have two issues. First of all, hydrogen has lower density compared to natural gas, so therefore we need more volume of hydrogen, and therefore this kind of shows an important role of line pack in order to meet secure, let's say, the supply demand balance in the hydrogen gas network. And also another aspect is that since we in the future in the net zero we should have significant amount of renewables, so this variability will be kind of reflected to the hydrogen system as well. And the reason is because of the link between these two systems, including the hydrogen-based power plants, electrically driven compressors, and also electrolyzers, which will play a major role in the green hydrogen production in the future. And therefore, these will kind of, let's say, make the interaction between these two very important and increase that. So therefore, it's of great importance that we kind of have this integrated analysis in order to kind of achieve the cost-effective transition to low carbon future. So that is kind of the components as an overview that we consider in our modeling, as probably mentioned so far, from hydrogen production, from blue, turquoise, green, then to electricity generation, different generation plants, and the transport is in our modeling on the pipelines, focus on the pipelines, having hydrogen storages, and modeling all the linkage between these two networks, and also having this electricity transmission system in different voltage levels, and other flexibility options and so forth will be kind of considered in the modeling. And just to, that's kind of the structure of the IHES model. Actually, we call it IHES, Integrated Hydrogen Electricity Systems Model, which is the IHES model. And for input, we have the spatial temporal demand data, capacity, location of infrastructure, operation costs, fuel prices, and so forth. And the objective function is to minimize the total operation and planning cost of both systems simultaneously. And that's an optimization kind of that we consider all the constraints and the operation and planning of both systems at the same time, considering these constraints. And the output would be the optimal power generation, optimal rear power and gas flow, gas pressure at different nodes, optimal location of hydrogen production technologies, and other just factors that can be as an output. So, and for this modeling, we kind of considered the GB network, as mentioned, and we kind of modeled which this also includes the offshore network, because we will have in the future significant amount of renewable offshore renewables, which so therefore that can be also a key important aspect to be considered, because we can also have the potential of producing the hydrogen offshore, the green hydrogen, let's say, and then just transport that to shore through the vessels or through the pipelines and so forth. So that's also another important aspect, that therefore we need to have this proper network for the offshore side as well. So kind of obviously these are two simplified networks. The left-hand side, you can see the gas network, which is an 85 node gas national transmission system, NTS plus offshore. And right-hand side, you can see a representative electricity transmission system of the GB, which includes 47 nodes. So the case study that we kind of use for this kind of presentation is that 2 heat decarbonization pathways on the 2050 net zero GB system based on the leading the way scenario of national grid has been used. And we have two options of heating, let's say two pathways: electrification, which is mostly on the heat pumps, which we call it ELEC. And the hydrogen pathway is mainly based on, let's say, having hydrogen-based gas boilers. And in the right-hand side, you can see that how the annual demand would be for the 2050, for example. In the ELEC pathway, we don't have any demand for heat, let's say, to supply the heat for hydrogen, but in the right-hand side, you can see it's 230 terawatt hour, which is kind of a big number that we kind of will support, let's say, supply the heat through the boilers. And in here, I consider two cases. Actually, one case is that we don't have this green hydrogen production, and the supply would be only based on the blue hydrogen and also the BECCS, and also the mixed case, which is having all options available. And just to see, kind of understand the value of, first of all, hydrogen in general, and more specifically the green hydrogen, that how this can kind of support the future decarbonization. So I just go through some results. First, in terms of the hydrogen supply, as you can see in these figures, the no green case, obviously we don't have any electrolyzers, so therefore we don't have any green hydrogen capacity or electrolyzer capacity, and the capacity would be mostly based on BECCS and blue hydrogen production in both electrification and hydrogen pathway. But as you can see in both of the kind of the mixed case, it's interesting that for the electrification pathway, we don't need to have any blue hydrogen production because the green hydrogen is doing a good job, let's say. And also the BECCS should be there because we need this negative emission technologies in order to kind of balance the carbon by the hard to decarbonize sectors. But in the hydrogen pathway for the mixed one, since the hydrogen demand is high, we need to have all these three main hydrogen production routes. And also in terms of hydrogen storage technologies, we just kind of made it as underground and overground technologies. LinePack is separate than this, but this is just the facilities. And here just we are kind of demonstrating that how much, let's say, in terms of capacity, terawatt hour capacity is required for the storage technologies in order to kind of, let's say, provide the flexibility that we need in order to supply the demand on time in the system. So just some hydrogen supply and demand numbers. Here is that actually how the production and the supply will be consistent, and it can be seen, for example, as expected in both when we have this green hydrogen production, the blue hydrogen production would be significantly decreased, and because we have kind of the supply from the green, which is obviously, this can have three reasons. First of all, we are utilizing the excess of renewables. So that is kind of zero carbon hydrogen production, very good. Then we have also some spatial limits on blue hydrogen production because as input, we have to inject natural gas to the plant. And since we don't have any more this natural gas transport infrastructure, we assume that all of these blue hydrogen production technologies would be close to the gas terminals. So therefore we bypass the the natural gas transport in the pipelines. And also another issue would be, since relocation of the blue hydrogen are limited, so we have also hydrogen transport issues due to the kind of the friction of the pipelines and so forth. So therefore we can see in both cases of mixed, the blue hydrogen production significantly decreased. And also here, just to show that we have a good supply from hydrogen-based power plants, which is this 37 terawatt hours, for example. Although, since in the hydrogen pathways, we have significant, let's say, already heat demand, so we don't utilize that much of hydrogen for electricity production. Then just in hydrogen network operation, I just try to make it quick. This is just to show, this figure in the bottom is just to show the kind of reflection of the renewable intermittency in the gas network operation. As you can see, that's the LinePack swings within the day. And so depending on here is, for example, 30 days are represented. And it can be seen that depending on the day and depending on the renewable variability, how much actually LinePack swing we could have. And this can go to up to, for example, 80 million cubic meters during the day we could have a swing, and in order to kind of keep the system work and supply kind of the demand in time. And then just some electricity aspects, as expected. I mean, obviously the electricity demand is increasing when we have this green hydrogen electrolyzers as a production, because obviously we need to put, let's say the input should be electricity, so the electricity demand is increasing. But the good thing is that actually we are integrating much better the renewables, and therefore you can see in both cases significant decrease in the renewable curtailment. So if, for example, in the hydrogen pathway, I guess that's going to be up to 80–85% decrease in the curtailment of renewable, which is a very good kind of, which hydrogen here is playing a very good role, because kind of we could produce that hydrogen when we have this excess of renewables, store it in the seasonal storages, and use it whenever it's required when we have low renewables and stuff. But from the other side, we need also have more response requirements. That is some frequency response due to the integration of kind of lowering the inertia of the system by integrating more renewables. So that's also one aspect that needs to be considered. And then just I summarize the key remarks. First of all, hydrogen plays a significant role in supporting the decarbonization of the energy system. When we have this green hydrogen, we have less dependence on blue hydrogen production, which can be good because the blue hydrogen should have also the CCS network, and that is kind of also have some limitations, and we need to consider that. The renewable intermittency will reflect in the gas network operation, which is therefore highlighting the importance of having this integrated analysis. So if we have electrolyzers, significant reduction in the renewable curtailment, and also hydrogen storage and line pipe plays a significant role in maintaining this supply-demand balance. And more response is required if we have electrolyzers, because we are integrating more renewables into this system. And I think that's it. I try to make it on time, 50 seconds more.
Very useful. Thank you very much. So thanks to both of our speakers for keeping to time, which does mean that we have time for questions now. So we have an opportunity to chat through and think about some of these issues that have been raised. So I'll maybe start and kick off with questions. So I wanted to ask Hossein, in the work that you've done, could you say a bit more about, for the electricity pathway, you've talked about more hydrogen storage being needed due to the hydrogen supply being less firm. Could you explain a bit about how you've defined what firm is and how much firm or less firm that means for the system?
Sure. Yeah, the reason is that, as I just presented, for example, in the electrification pathway, when we have green hydrogen, we don't need any supply from blue. Blue is actually the firm hydrogen supply that I was talking about, because as long as the natural gas is available, so I can just produce the blue hydrogen, so there shouldn't be any problem. But since I'm using mostly green hydrogen, and as we know, the green hydrogen is kind of directly related to the renewable variability. So therefore, I'm kind of reflecting again let's say the green hydrogen supply comes with the variability of the renewable. So therefore, I need to have more hydrogen storage in order to kind of capture whenever I have this excess of renewables, producing the green hydrogen, store it, and use it whenever it's required. When, for example, I have the cases of low renewable, high demand, this hydrogen storage can play a significant role in enhancing the resilience of the energy system. So therefore, that's the reason that I just mentioned this. Yeah.
Okay, thank you. And I'll also ask a question for Harry. So Harry, in terms of the techno-economic evaluation work that you did, I thought it was quite interesting that you could show how economically viable some of these systems were, provided that hydrogen prices were at around £3 a kilogram, but you showed the levelized cost of hydrogen varying between 1.9 and I think it was £2.8 per kilogram. How does that value compare with the cost of carbon? Because obviously you've got a process that enables you to produce hydrogen, but also to capture the carbon. So if you weren't doing the carbon capture, then what would the carbon value or the carbon cost add if you weren't doing that process?
Yeah, so for the level cost of the hydrogen based on the UK, because as I mentioned, it's about 1.8 to 1.9 to 2.8. So this is for level cost of hydrogen, and this is on the UK base, because if we do another country, it will have a different value, because the level cost of hydrogen, when you do the sensitivity analysis, you can see the fuel cost is the most important factor to affect the level cost of hydrogen. So if we have a country that have a cheaper natural gas, so the level cost of low carbon hydrogen is even lower. And for the CO2 avoided cost in the UK case, so if we have the carbon price, so the cost will be negative, because you sum of the case, you capture more CO2 if you use the biomass biomass, and then you actually can earn money if you have the carbon price. If, for example, I assume the 16 pound per kilo of CO2 captured, but if we don't have that carbon price, if we don't assume we have the carbon price, so the cost is for the ICS smart process is about 30 pound per kilo of roughly 30 to 80 pound CO2 captured for the ICSMR process. So which is comparable to some when you use the ISMR with the MEA for the amine-based solvent capture. So it's even lower. So some of them, because the model is based on your assumptions, so but most of the ICMR case have a lower CO2 avoided cost or removal cost compared to the SMR with the MEA solution. So yeah.
Great. Okay, I'll hand over to the audience and just check if we have any questions, if people want to use the raise hand function or type in the chat. Shahab, thanks.
Yeah, thanks. Very nice presentation. I got a question from Hossein, if possible. My first question is about the tool that you have used here. Very curious about it. Is it vSIM or iOS or another tool? And the other question is about actually extreme conditions, extreme weather conditions. If you have done any analysis based on extreme, weather conditions, and if yes, how? Thank you, Hossein.
Yeah, thanks, Shahab. Well, actually, that is, as I mentioned, the model is called IHES. It's a complete different model than IVES or vSIM or something. That's something that I kind of working myself on, and kind of I developed this from my PhD based on the CGen model, which I was working with Mason on that. Yeah, that's the model. But yeah, in this scenario, because when I'm modeling the whole year, I assume 30 representative days, and 2-3 of these days are kind of been modeled as extreme conditions, which is a very low renewable high demand and also even high renewable low demand. These are also included in the model just in order to understand what should be the value of this hydrogen line pack storage and so forth to enhance the resilience of the system. Yes.
Thanks.
You're welcome. I've got a quick question for Harry, by the way, if it's okay.
Yes.
In terms of the enhanced SMR plan that you just mentioned, what's the expected efficiency that you want to reach? And
I think it's very similar. The overall efficiency is very similar to the ISMR. It's about 66 to 76 to 79 for the 90 efficiency. So I think the overall efficiency is probably very similar to the ISMR process, but the unique for the sorption enhanced or chemical looping is to reduce the additional size or footprint for the ISMR, because you don't need the water gas shift reactor and also the pressure swing. So that probably you have the lower OPEX and CAPEX and low CAPEX and OPEX. So I think
technically you also need less CCS infrastructure in order to capture the carbon, right? If you use this.
Yeah. So you don't need to use the MEA process. So that I think is very unique or very advantage for this kind of technology. And also this technology has been a pilot plant has been built in Cranfield University for 1.5 megawatts. So which validate them from TRL4 to TRL6. So which is, I want to see some results from those projects, which maybe can give a little push for the ICMR to apply it in a large scale for low carbon hydrogen production.
Okay, thank you.
Great. Well, that seems to be all the questions that we have for our two presenters today. So thank you very much, everyone, for joining. We will let you know once the recording is uploaded so that you can share that through your own channels as well, and make people aware of the presentations that we've had from both Harry and Hossein on these possible cost-effective solutions to improving the role of hydrogen in our overall energy systems. Thanks both to our speakers, Harry and to Hossein. Thank you very much. And we'll be in touch to let you know about the recording. Thanks again, everybody.
Thank you,
have a
everyone.
good afternoon.
Thank you, everyone.
Yeah, have a good day. Yeah,
Thank you.
Thanks.
Bye.
Bye-bye.
Bye for now.